Okay, so we'll begin. Are there questions?
So,
Yes, go ahead, please.
is there a means to solve, let's say, the 5-4 theory? Like we have one perturbator means. Do we have non-perturbative means also that give us the same results?
Well, for 5 to the fourth theory, there is really no non-perturbative techniques. Right? Okay, the general non-perturbative technique that people use is in putting it on a lattice. But this requires a theory to be, there is some specific property of a theory that is needed, which is called asymptotic freedom. And 5 to the fourth theory is not asymptotically free. Right? So you cannot just take 5 to the fourth theory and put it on a computer. Okay, putting it on a computer, of course, you can always do. The question is ultimately whether you can take the limit when the lattice spacing goes to 0, right? Which is called a continuum limit. So as far as you know, 5 to the fourth theory really doesn't have any non-perturbative means. You have to use perturbation theory.
So, in
But
some other theory, do we have like a comparison for perturbation and non-perturbative results? I'm saying.
yeah, in QCD, for example, you can put it on a lattice and then you can try to match up with some perturbative results.
So, do the S matrix elements agree? Like,
Well, see, you cannot calculate the S matrix elements exactly on a lattice, right? Because lattice basically you do numerical. You put it on a lattice and then you simulate, right? And in QCD, of course, the usual S matrix elements are not there, right? Because the elementary fields, the quarks and gluons, are not physical particles. They do not represent physical particles, right? So that in QCD, the physical particles are like protons and pions, which are not, whose corresponding fields are not there in the Lagrangian. Right? They are all bound states. So
okay.
in that sense, you cannot directly compare the S matrix and see if they agree. But there are some things that you can test, right? That whether they match up in an appropriate domain where the lattice results and the perturbative results are both valid, you can ask if they match or not.
Some other observables, you mean?
Yeah, it's not like, yes, uses some other observables, yes.
Okay. Also, if we go back to this definition of mass that we are giving, like the pole of the 2 points Green's function,
Yes.
the way we are sort of stating it in some interacting theory, it seems like we are specifically relying on the perturbative expansion.
No, not really. Because when he saw that it's the pole of the 2-point Green's function, here we didn't use any perturbation theory, right?
I mean, in an interacting theory in general, for strong coupling where we don't have perturbative results,
Yes.
we will still define the mass as the pole.
Yeah, pole of the two-point Green's function, exactly. Right? Because what you saw is that you took the 2-point Green's function. In fact, we didn't even have to take the fields as the elementary fields, right? As he emphasized that instead of taking phi, for example, you could take phi squared, phi cube, anything, any operator, calculate the 2-point Green's function. And then what we relied on is that if there are single particle states, right? Single particle states by definition are the ones for which there is a definite relation between energy and momentum, namely E
Yeah.
squared E squared plus M physical square. We simply assume that those particles propagate in the intermediate state, right? We calculated their contribution to this 2-point function. And then we found that in the momentum space, this produces a pole in the 2-point function. So that part didn't use any perturbation theory. Perturbation theory came later when he said how systematically in order by order in coupling, we'll calculate this, right? Then we introduce this one particle irreducible amplitude and showed how to calculate it systematically, right? The relation between MP and M. But the definition of MP, the fact that MP is that pole of the 2-point Green's function, that doesn't rely on perturbation theory.
Okay.
Yeah, that part was completely general. Let me see if I can go back there. I'm not sure which lecture it was in. Let me okay, yeah, lecture 24 here. Okay, so we introduced this G plus. This could have been any Green's function, right? This phi could have been any operator. And then we derived this form. This didn't require that this is phi, right? Or in any perturbation theory, right? This came in the earlier. We basically this is just you introduce a complete set of intermediate states, right? And then we looked at the effect of the single particle states. Let me see where that is. Yeah, this is also completely general. Yeah, so this is where we started considering single particle intermediate states, right? The sum prime, sigma prime means it's sum over single particle states, right? And all we use the fact for the single particle state was that they are labeled by this momentum P, and their energy is fixed in terms of momentum. And then rest of this phi could have been any operator there, right? I mean, we didn't even, there is no reason why you have to demand that this is the field that enters the Lagrangian. And then the rest of the analysis goes through, right? There's general properties of Lorentz invariance and so on. So this is, so the fact that it produces a pole in the two-point function, that's completely general. Right? And in fact, in lattice gauge theory, for example, when you try to calculate the mass of the proton, you basically take appropriate two-point function and look for the poles, where the poles are.
Okay.
Are there other questions?
Sir?
Yes, go ahead, please.
Yes,
Go
sir.
ahead.
Regarding that quantization of electromagnetic field.
Yes.
If we have started with any like any other gauge or any in general any gauge, then still we would be able to describe the theory using only the two fields, two independent components of A.
Yeah, the point is you may have more than two independent components, right? In Feynman gauge, for example, you have all four independent components. But ultimately, the physical states will still be labeled by two independent index, two independent polarizations.
Yeah, and that's because photon is massless and it can have the two physical polarizations.
Exactly, yeah. But that you see explicitly in the theory. I mean, it will come out of the theory, right? Even if you use Feynman gauge, for example, where there are four fields, you'll eventually see that after there you have this additional condition called the physical state condition. And after you impose all that, you will still find that there are only two independent states for every momentum. Okay, which is the polarization of the photon.
Okay, so if in that Feynman gauge, if we use the Feynman gauge for virtual photons, then we will have all four independent degrees of freedom, right?
Yes, except that you can show by appropriate decomposition that of those four independent degrees of freedom, okay, only two will contribute.
Only two will contribute if it turns out to be a real.
In the S matrix.
Okay.
In a Green's function, everything will contribute. But when you go to the S matrix, okay, only two will contribute. Let me see if I had briefly indicated this earlier. Let me go back to file. Yes, here I had said I don't know where I have. Yeah, I think this is where I had said that in the Feynman gauge, it's the theta mu, right? The difference between these two, between Feynman gauge and the Coulomb gauge, are all these terms, of which this term is just the contact interaction, the JJ interaction, which cancels at the end. This part actually vanishes for the S matrix, right? If you look at the contribution of this part to the S matrix, right, after summing over graphs, this actually drops out. And that's the way we show that in the Feynman gauge or the Coulomb gauge, right, the virtual particles, right, these are the propagator of the intermediate particles. They eventually give the same contribution. Even though in Feynman gauge all four fields are present.
Okay. Sir, another thing.
Yes.
Can you give some reference on QCD Lagrangian and the development of this S matrix and perturbation theory? the QCD perturbation theory?
I think any book on quantum field theory should have it, right? Which has non-abelian gauge theories.
Okay.
That will also have QCD.
Okay.
Right? I think yeah. So and it will be taught, of course, in the second QFT2 course in detail.
Okay.
Weinberg's book, for example, will certainly have great, discussion in great detail of non-abelian gauge theories. Are there other questions? Okay, so if not, let me proceed. Okay, so what I'll do, I'll first begin by reviewing the last slide of last lecture, okay, with the collection of all the results, okay, and then we'll proceed from there. So what we had done last time was that we found an expansion of the Dirac field, okay, which is given here. This is the normalization factor over here. Okay. And then we have these two operators, B and D dagger. B is the annihilation operator for one kind of particles. D dagger is the creation operator. Okay. And the reason that they appear asymmetrically is because to begin with you had a B and a C. Okay. But then you saw that if we think of C as the annihilation operator, okay, then it has this strange feature that C dagger, okay, apparently it creates a particle but it lowers energy, right? That doesn't sound sensible. So then you said that, okay, let's declare C as D dagger and C dagger as D. The anti-commutation relations remain unchanged. Okay, so now it's possible to think of D as the annihilation operator and D dagger as the creation operator. And that's why these two things appear asymmetrically, B here and D dagger here. And U or V are just fixed functions, okay, which solves Dirac equation. So then by looking at the anti-commutation relation of the psis and the psi daggers, okay, we derive these anti-commutation relations. So B, B dagger have the standard anti-commutation relation of a creation annihilation operator. Similarly for D, D dagger, okay, these are formulaic, of course, okay, that's why there is an anti-commutator. Okay. And everything else vanishes. So for example, B and D dagger anti-commutator vanishes, D and B dagger anti-commutator vanishes. And then all the annihilation operators anti-commute themselves, and similarly all the creation operators also anti-commute themselves. And then in terms of these operators, we wrote down the expression for the Hamiltonian, okay, which is here. Okay. Now, earlier there is an extra minus sign, okay, between these two, okay, which came from the fact that EP, when you solve Dirac equation, you get solution both with positive energy and negative energy. Okay. But that we overcame by simply declaring C as D dagger and D dagger as C. Okay, that's why this sign has become plus. And then we said that the momentum operator also takes this form in this language. This I didn't prove, but I left it as an exercise for you to check this. And given these two, okay, now you see that B does act as an annihilation operator. It lowers energy. B dagger increases energy. Similarly, D lowers energy. D dagger increases energy. Okay. So you define the vacuum state as the one that is annihilated by both B and D. And then we can create particle-like states by simply applying B daggers and D daggers on this. So in particular, the single particle states are obtained by a single B dagger or a single D dagger. So you have four types of single particle states. These are B dagger on vacuum, okay, with S taking values 1 and 2, and D dagger on vacuum with S taking values 1 and 2. And all of them, of course, have the same relation between energy and momentum. Namely, EP is square root of P square plus M square. So this shows that all four particles describe particles of the same mass. Okay, the mass is given by square root of EP square minus P square, that's M. So this is where we had ended last time. And our first goal today will be to find physical interpretation of these four states. Okay, what do these four states physically represent? But before I go on, are there questions on this? These results are clear?
Sir, any theory that we make, we have to put in Is it if the particles are fermionic or bosonic by hand?
Yes, at this stage we are putting in by hand, right? But there is a general theorem which is called spin statistics theorem, which says that if you want to find a consistent quantum theory, right, then you have to put in anti-commuting relations for the spin for particles of spin which are integer plus half, and commutation relation, right, commuting fields for particles whose spin is integer. But this is something that we have not certainly proved, right? This is the general result. So it's not, so eventually we really don't have the freedom. But at this stage, we are just putting in by hand. Okay, that they satisfy anti-commutation relation instead of commutation relation. But eventually one can show that if we try to put commutation relation here, we'll run into trouble. One thing you can already see, right? That if we had put commutation relation, then you cannot simply declare C as D dagger and D as C, D and as C and C dagger as D, right? Because the reason that we could do this, right, replace C, interpret C as D dagger and C dagger as D, is because the anti-commutation relation between C and C dagger are perfectly symmetric, right? You could replace C by D dagger and D dagger by C, and they preserve its form, therefore. But if we had imposed a commutation relation, C dagger commutator is 1, say, right, or it is delta Q P minus P prime. Then if you declare C as D dagger and D dagger as C, then we will get D dagger D anti-commutator is delta Q P minus P prime. But that's of course not the correct anti-commutation relation between the annihilation creation operators, right? It should have been D dagger anti-commutator is delta Q P minus P prime. So that's one place where you can see that things will go wrong if you try to quantize using anti-commutation relation here, using commutation relation. But as I said, this is part of a more general result, which is called the spin statistics theorem, right? Which correlates the spin of a particle to what statistics you can put. Is this clear?
Yes, sir.
Any other question? Okay, so let me proceed. Okay, so now we are going to try to interpret these 4 states. Okay, and we'll do this again by invoking symmetries of the problem. So to do that, we notice the Dirac action is invariant under this phase transformation. Psi goes to e to the I theta times psi, and psi dagger goes to e to the minus I theta times psi dagger, because it has the form of psi dagger times something, some operator times psi. Okay, same as what happened for the Schrodinger theory. This symmetry was in fact present also in the Schrodinger field theory. So because of this symmetry, there will be a conserved quantity, and we can easily calculate the conserved quantity. In fact, the calculation of J0, okay, which is needed for the charge, is identical to what we had for Schrodinger theory. Okay, we just apply the standard Noether procedure. So I leave this as an exercise. Okay, in fact, you can just look at the derivation for Schrodinger theory. That the corresponding operator we had in fact called the number operator. Okay, here it will not be number operator, but we denote it by n nevertheless. Is given by integral dq bar psi dagger psi. And then when you expand psi, when you substitute these expansions, you have psi in terms of these variables. And by using appropriate normalization condition on the u's, you will find that this n is given by integral dq p times b dagger b minus d dagger d. This minus sign here came because of the fact that in the expression for psi there is a d dagger and a b. So when you take, for example, psi dagger psi, right, this gives you b dagger b, okay, which is comes with plus sign. This, on the other hand, will give you d dagger, which you can write as d dagger d, but with a minus sign. Okay, and the constant piece you are always ignoring. Okay, this should be understood that anytime there is a constant added to any charge, you can just throw it away. So d dagger you can write as d dagger d. or sorry, d dagger you can write as minus d dagger t using the anti-commutation relation. Okay, so is this clear? Okay, this is just a straightforward exercise to evaluate this. But from the structure, we see that if we now apply this n on the state B dagger acting on vacuum, then n has eigenvalue 1 because this commutator of this with B dagger is B dagger, and on this state, okay, because of this minus sign over here, it has eigenvalue -1. So this tells us that there is some conserved charge which takes value 1 for the states B dagger acting on the vacuum, and which takes value -1 for the states D dagger acting on the vacuum. Now, how to interpret this charge is of course up to you, right? Depending on what theory you are trying to consider. But our interest will be in the theory of electrons and positrons. So we'll try to interpret this as the electric charge, okay, or as something proportional to electric charge. So in particular, if -e denotes the electric charge that is carried by the electron, then we'll define the electric charge operator as -e times n, which given this takes the form -e times integral d cube p times b dagger b minus d dagger d. And so now this charge q has eigenvalue -e for the states b dagger on the vacuum and +e for the states d dagger on the vacuum. So given this, now you can see that you can interpret now this b dagger on the vacuum as the state of an electron, okay, single particle electron state, single electron state, and d dagger on the vacuum, because it has positive charge E, this can be interpreted as the state of a positron. Now I should say that this of course seems quite natural today, but when Dirac equation was first written, the positrons were not even discovered, right? In fact, Dirac equation predicted the existence of positrons. But now that we know electrons and positrons exist, okay, it's quite natural to interpret these kind of states as electron states and these states as positron states. And that's the way we'll interpret this in electrodynamics. Are there questions? So I leave this as an exercise to calculate the full conserved current. Okay, this calculation is slightly different from the Schrodinger problem because the spatial part is different, of course, right? In the Schrodinger problem, we had p square by 2m, right? Or in terms of operators, it's a gradient square. Whereas for the Dirac equation, the operator was gamma I pi, okay, or gamma I del del xi. So because of this, the actual form of Gi is different. J0 is the same, but Gi is different. And I leave it as an exercise for you to check the J mu, the full conserved current for the symmetry is given by -e times psi bar gamma mu psi. This of course reproduces back the correct Q. But this whole J mu will be important for us when we try to couple it to electromagnetic field. Because since this now has the interpretation as the electric current in this theory, we know that in Maxwell's equation, for example, J mu, the electric current, J mu appears on the right hand side of Maxwell's equation. And we had also written down the corresponding Maxwell action, the term in the action, which produces that J mu term on the right hand side of the Maxwell's equation. So this will be useful when you try to couple electromagnetic field to a Dirac field. Okay? So basically, we'll modify the Lagrangian in such a way that Maxwell's equation has precisely this appearing on the right hand side. But for now, we'll just proceed with free Dirac theory. Okay, keeping in mind that we can define J mu in this way. Okay. Are there questions? Okay, so now we have to find the interpretation of the label S. right? Because we had seen that the state is labeled by two, the additional index S, which takes what values 1 and 2. And we may now ask, what is the interpretation of that label? And to find the interpretation of this label, we have to study the conserved charge associated with the angular momentum. Okay, because this level actually will turn out to be the spin level. Okay, and what I'll do, I'll not give the full derivation, but what I'll do is that I'll state the results, and I'll leave it as an exercise for you to actually check this. Okay. So let me remind you how we calculate the angular momentum operator in a general theory. So if you remember, we had started with a generic theory with a set of fields, phi r. Okay, we didn't say whether the phi r's are scalars or they're components of a vector or they're something else. But we have taken a generic theory with fields phi r. And for such a theory, the infinitesimal Lorentz transformation takes the following form. Okay, so the transformed field phi tilde r is given by phi r, and then there is a term that is responsible for the change in the argument of x. Okay, for finite transformation, basically phi tilde r of x has phi r of lambda x. Okay, and then there is a matrix S that was multiplying from outside. That lambda x part, right? When you try lambda as identity plus a infinitesimal matrix, okay, that part after you Taylor series expansion gives you this. And this part is basically came from the matrix that multiplies phi. Okay, the infinitesimal version of that is this one. So let me remind you of the notation. So omega was an antisymmetric matrix. This came from this is the infinitesimal Lorentz transformation parameter. So this epsilon, okay, epsilon is the infinitesimal parameter. Omega are the coefficients that multiply epsilon. So omega was antisymmetric. Okay, this is what we had found for Lorentz transformation. Okay. These are some fixed matrices. Okay. What these matrices are, of course, depends on what theory you are considering. Okay. These matrices basically came by expanding that matrix S that was multiplying phi, okay, for a finite transformation. Okay. So this is what I have said here, that these are specific constants that encode the Lorentz transformation laws of phi r. Okay. So in particular, if you are dealing with scalars, then these are just 0. Okay, because for the scalars, this is the full transformation law. Okay. For vectors, you can find what these are. Okay. And our goal will be to understand what these are for the Dirac scalars, for the Dirac fields. So given a transformation like this, which is a symmetry of the action, we had then derived the corresponding conserved quantities. And the conserved quantities had this form. Okay, it's the integral of the angular momentum current. You have the zeroth component of the angular momentum current, m0 nu tau. And m mu nu tau, okay, was given by this. This is what we had identified as the orbital part of the angular momentum operator. Okay, or orbital part of the Lorentz generator. These are angular momentum, but it also has the boosts. So this was the generation of the orbital part of the operator, and this came from the spin, right? Because this, as you can see, depends on sigma. So in particular for scalars, this will be absent. So this was a general story. Now what I'm going to do is to state what the corresponding story is for the specific case of Dirac fields. But are there questions on this? So this is basically what we had done earlier. In case you have forgotten, just you can go back to your notes and look up the formulae. Okay, and this is the formula that we had found. Okay, so now I'm going to leave you with some exercises. So the first exercise is to show that the Dirac action is invariant under Lorentz transformation, provided we choose the sigmas appropriately. And the particular choice of sigma, see, sigma now will have, of course, tau nu index is there, right? These run from 0, 1, 2, 3. Instead of RS, okay, RS was the field levels, here you have alpha beta, right? Because Dirac spinner, the Dirac field carries this index alpha. Okay. So we are looking for what is sigma tau nu alpha beta here. And the claim is that for an appropriate choice of this constant C, this is what leaves the action unchanged, invariant. Okay, so sigma tau nu alpha beta is given by C times gamma tau gamma nu minus gamma nu gamma tau alpha beta. This is matrix product. So your task is to find this constant C. And the way you will find this constant C is simply by demanding that the action remains unchanged when you make this transformation. Okay, as given here. Okay, so is this statement clear to everybody? Okay. So once you have found sigma, right, then you can just use this formula. Okay, we know what the action is, okay, or the Lagrangian is. So you can calculate J mu nu. Then using this J mu nu, we can construct this operator. Right? This operator, see, remember that epsilon ijk jjk, this is basically the angular momentum along the ith direction. And you are taking the inner product of that with P, right? So epsilon ijk pi jjk, which basically means that you are taking the component of the angular momentum along the momentum. And this we normally do, okay, as we had discussed even for the photons. The reason that you look at the component of the angular momentum along the momentum of the particle is to get rid of the orbital part, right? Because the orbital part of the angular momentum has no component along the momentum, right? It's after all r cross p, right? So its inner product of p is 0. So that's why this operator is useful. This is also sometimes called the helicity operator. So helicity is basically measuring component of the angular momentum along the momentum. Normally, you would also normalize by mod p, okay, but I have not written that here. So this is straightforward once you have constructed J nu tau. And then the next task is to show that if we consider, for example, the state B0 PS dagger or vacuum and apply this operator J, then by taking appropriate linear combinations, these combination of these states, see here S of course is a label that runs over 1 and 2, right? This label came from the degenerate eigenvalue problem of the Dirac equation. But now the claim is that by taking appropriate linear combination of these two states, we can get eigenstates of this operator J. Which particular two states, okay, of course, you have to find. But the important point is that the eigenvalues of J are given by plus minus mod p by 2. So if you divide by mod p to normalize, the eigenstates, eigenvalues are plus minus half. And this basically establishes that the electrons have spin half. Because a spin half state can exist in two spin states along a given direction. Here the direction we have taken to be along the direction of the momentum, just so that the orbital part doesn't contribute. And then we can show that electron by the fact that these eigenvalues are plus minus half, okay, after they have divided by mod p, it follows that the electrons have spin half. And we can do a similar analysis involving these states, and that in turn so that the positrons have spin half. Okay, are there questions? In fact, we made a similar statement also for the photons. That also I would advise you to work it out in detail. Okay, construct the angular momentum operator for the electromagnetic field, okay, and check that indeed when you calculate the analog of this operator J, that you get the correct eigenvalue. Okay, are there questions? And independently of this, I'll leave it as an exercise also to show, okay, that this is a useful property that under Lorentz transformation, psi bar psi transforms as a scalar, and psi bar gamma mu psi transforms as a contravariant vector. In fact, these relations you will probably have to prove anyway when you are going to check that this leaves the Dirac action invariant. Because Dirac action involves say m psi bar psi, right? Which better be invariant, right? That will happen if psi bar psi transforms as a scalar. And it also involves psi bar gamma mu times del del x mu of psi. And that is invariant if this transforms as a vector. So these you can also check independently. Any question? Okay, so if not, let me proceed. Okay. So this is as much as I'll say about the spectrum. Okay, so you have now found the interpretation of the spectrum, okay, that you have 4 states to begin with, 4 single particle states. 2 of them are electrons, okay, and that 2 refers to the fact that electrons are spin half, so it can exist in either spin up or spin down state. Okay. And the other 2 are positrons. Positrons also have spin half, and hence they can exist in spin up and or spin down state. Right? That's the explanation of what these 4 states are. Okay, so our next task will be to calculate Green's functions. And we'll be focusing on Green's functions of time ordered product of operators. Because first of all, that's easy to calculate, that's simpler to calculate, and also because that's what enters the expression for the S matrix. So we'll begin with 2-point function, time ordered product of psi alpha of x1, psi bar beta of x2. So this is defined in the usual way, except for one difference, that because these fields are fermionic fields, we define the time ordered product with an extra minus sign when we switch the operators. So when T1 is larger than T2, okay, then the operators are in the order psi alpha of x1, psi bar beta of x2. Then you just write as psi alpha x1, psi bar beta of x2. When T2 is larger than T1, then psi bar beta has to go to the left, okay, which is what has happened here, except that you also put a minus sign. Okay, that's the convention in which you will define the time ordered product for fermionic operators. Okay, is this definition clear? Okay, so once you have given this definition, okay, our next task will be to calculate the propagator, okay, which I'll denote by SF alpha beta. This is the analog of the delta F, the x1, x2 that we calculate for the Klein-Gordon field, okay, or d mu nu that we calculate for the photon. Okay. Here we will denote by SF alpha beta x1, x2, okay, which is simply the vacuum expectation value of the time ordered product of psi alpha of x1 and psi bar beta of x2. Notice that for most purpose we are going to use psi bar. Psi bar, let me remind you, is just psi dagger gamma 0. I could have also used psi dagger, but psi bar is a more convenient thing to use. Okay, so we'll be always using psi bar. But once you have for psi bar, you can of course multiply the whole thing by gamma 0 and get back the expression for psi alpha of x1, psi dagger beta of x2. Okay, so this is what I have said here. Okay, this is something you should keep in mind. Okay, so now the calculation of this will proceed as in the case of scalar field theory. So let me give you the steps that you will do. So the first thing to do, you see, we have to put psi alpha of x1, psi bar beta of x2, and the expansion of psi is was given here. Okay, so this is the expansion of psi. Okay. So the first thing we'll try to do is to write these in terms of b at time t equal to 0, d at time t equal to 0. Okay. Because once both have been made time t equal to 0, okay, then you can use equal time commutation relation, right? Because to begin with, we had psi at x1, psi bar at x2. Right? So the time arguments are not the same, so you couldn't use equal time commutation relation. But if we can write everything in terms of the operators at 0 time, then of course we can use equal time commutation relation. And this is what we have done also for Klein-Gordon theory. So to do that, we'll use these commutation relation. H with B is given by minus EP times B. Okay, H with B dagger is EP times B dagger. These are more or less identical to what we had for Klein-Gordon theory. Okay, except that B, instead of B, we had an A and A dagger. So similarly, H with D is minus EP times D, and H with D dagger is EP times D dagger. So using this and using the Heisenberg equation, we can solve for B, time dependence of B. So B at time t is given by B at time 0 times e to the minus I EPT. B dagger is of course complex conjugated, so it becomes e to the plus I EPT. Similarly, D at t is D of 0 times e to the minus I EPT, and D dagger at t is D at 0 times e to the I EPT. So here all I have done is that I have taken the expression for psi and psi bar that we had earlier, or the expression for psi that we had earlier in this equation, and simply substitute for B of t ps as B 0 ps e to the minus I EPT, right? Just from here. And similarly for D dagger. Now to get the expression for psi bar, okay, psi bar is psi dagger gamma 0. Okay. So these of course remain unchanged. Okay. So because it involves a complex conjugation, okay, so B becomes B dagger, e to the minus I EPT becomes e to the I EPT, and U alpha becomes U dagger times gamma 0, that's U bar. So remember that the Dirac index, the alpha beta index, okay, are carried by U and U bar, okay, but B does not carry any alpha beta index. Right? B or D doesn't carry any alpha beta index. Okay. So that multiplication by gamma 0 has to happen with U only. Right? So U gets converted to U bar. Similarly here, the complex conjugation makes D dagger into D, okay, this into e to the minus I EPT, and V into V dagger gamma 0, that's V bar beta. So the idea is that we take these expressions for psi and psi bar, okay, and just substitute here. So we substitute here, okay, because everything is written in terms of the B and D and B dagger and D dagger at the same time. Okay, you can use the standard anti-commutation relation, okay, to bring the B's to the extreme right, okay, and the B daggers to the extreme left. Similarly, D's to the extreme right, D daggers to the extreme left. Okay. Then use the fact that B and D annihilates the vacuum to the right, and B dagger and D dagger annihilates the vacuum to the left, okay, to simplify the result. Right? Again, the same analysis as in the case of Klein-Gordon theory. And this is what we get. Okay, and then you also use the expression for U and V. Okay. So U PSR, for example, was given by this expression over here, e to the I P dot R over 2 pi to the 3 half times UPS. Okay. So this was defined as some solution to some eigenvalue problem. And similarly for V. So I leave this as an exercise for you to check, okay, that when you do all that, okay, then SF has an expression like this. Let me just point out some features over here. So you see, in SF was given by this expression, time order expectation value of the time order product, and time order product has this structure, right? So for T1 larger than T2, you see that psi alpha is to the left of psi bar beta. So when psi alpha is to the left of psi bar beta, then of course the B, okay, so the term that contributes is the B dagger term. Okay, because B dagger you have to convert to B dagger B, you have to pick up the anti-commutator, because then B acting on the right gives you 0, B dagger acting on the left gives you 0. Okay. So when psi is to the left of psi bar, then this is the term that contributes, okay, this pair. This pair, on the other hand, doesn't contribute because here D dagger is on the left, D is on the right. That already is 0, right? Because D acting on the vacuum will give you 0, D dagger acting on the vacuum on the left gives you 0. So for T1 larger than T2, it's this pair of terms which contribute. Similarly, for T1 less than T2, okay, when psi bar is to the left of psi, then of course this term doesn't contribute, neither does this, but this pair contributes. And that's what you see this structure here. So when T1 is larger than T2, then psi is to the left of psi bar. So then the U's come. And when T2 is larger than T1, then psi bar is to the left of psi, and then the V's come. Okay? And you can check all these exponents work out correctly. Are there questions? Okay. So now I'll define this operator P slash, which is a very useful notation, and you will use it many times. Which the definition is simple. In fact, it's just minus P dot gamma, or minus eta mu nu gamma mu P nu. So when you expand in components, is the gamma 0 P0 minus gamma dot P. And this has a useful property that if you take the square P slash times P slash, okay, which you can of course write using this, because this is minus P mu gamma mu, the P slash times P slash is P nu times gamma mu gamma nu. Now because this is already symmetric under mu nu exchange, I can replace it by P nu times half of gamma nu plus gamma nu. I have symmetrized it. And now you can use the fact that this combination is just minus 2 times eta mu nu. So using that, you just get this to be minus P square. So P slash square is minus P square. So this is a result that we will use. There are some other results that we will use, which I will not prove, but you can find them in standard textbooks on relativistic quantum mechanics. Okay, these are the various relations involving U's and V's. So the first relation is that if you take U alpha PS, U bar beta PS, and sum over S, you get something like this. This is some analog of the completeness relation. It's not exactly completeness, but some analog of completeness. Here P0 is EP. M, of course, is just number. So M alpha beta is just M times the identity matrix, M times delta alpha beta. Similarly, if when you take the sum over S of V alpha times V bar beta, you get 1 over 2M times P slash minus M alpha beta, again with P0 being equal to EP. The other useful relations are U bar U is delta SS prime, and V bar V is actually minus delta SS prime. Okay, that's the way I have written it here. And U bar V is 0, V bar U is 0. Again, as I said, these are standard identities involving the solutions to Dirac equations, and in the way you have normalized it, but I'll not try to prove them here. Okay, you can just look up standard textbooks on relativistic quantum mechanics. Okay, are there questions or comments? Okay, so with this, let's see what we get. So here, all you have done here is that the sum over S equal to 1 to 2 U alpha PS U bar beta PS, right? I have just replaced, I am replacing it by P slash minus M alpha beta, right? 1 over 2M times P slash minus M alpha beta. So 1 over 2M, okay, so what happened to 1 over 2M combined with this M over EP to give you 1 over 2 EP. Okay, that's what is here. And then this is P slash plus M alpha beta. So, and similarly for sum over S of V, okay, I replace it by 1 over 2M times P slash minus M alpha beta. So that's here. And the minus sign here, okay, of course, should be clear, it's inherited from the original minus sign, right? This minus sign is in part of the definition of the time ordered product. Okay, are there questions or comments? Okay, so now the claim is that this is given by this. Okay. This analysis is in fact more or less identical to the case of Klein-Gordon theory. Okay. There, of course, you didn't have all these P slash plus M alpha beta terms. Okay. We had an H T1 minus T2 of this, and then H of T2 minus T1 times an appropriate exponent. Here the only difference is this extra term. Okay, so let me just explain how this comes about. Okay, so in this expression over here, this term that you see p slash plus m alpha beta, this term here p0 is not EP. Okay, p0 is independent because here you are doing a full 4-dimensional integral. So what happens is that this denominator here is p0 square minus EP square plus I epsilon. So p0 has poles at plus minus EP with appropriate I epsilon shift. So when you carry out this integral, right, when T1 is larger than T2, for example, then you can show that in order for this to be convergent, you have to close the contour in the lower half plane. And when T1 is larger than T2, T1 is less than T2, you have to close it in the upper half plane. So in the first case, you pick up the contribution from P0 equal to EP, and that gives you this term. That just converts this P slash plus M into P slash plus M, okay, where P0 with P0 set equal to EP. When T1 is less than T2, that is this term here, then you have to pick up the pole at P0 equal to minus EP. So that in this P slash, then it just gives you minus EP. For P0, it gives minus EP. And then what you do is that you also change. See here it's IP dot x1 minus x2, right? Here you have a minus IP dot x1 minus x2. So you also change variables from P vector to minus P vector. So that basically makes this into minus P slash, where now P0 is equal to EP. I'll leave this, I'm saying this in words, but you should just work it out yourself. So that P vector to minus P vector is necessary in going from here to here, that change of variable. And then you get basically minus P slash plus M, which becomes P slash minus M with a minus sign. So this expression over here is exactly this, okay, after you do a P0 integral. So this, please try to check explicitly. Okay, are there questions? So this equation we can also write in a slightly different way, which is here. This is the matrix inverse. And the reason that we can write it this way is because of this identity that if you take P slash plus M times P slash minus M, then you expand it out. P slash times P slash gives you minus P square from this relation over here. Cross terms cancel because you get a minus M P slash and an M P slash. And of course, there's a minus M square. So you get minus P square plus M square. So this tells us that P slash plus M over minus P square minus M square is P slash minus M. So, sorry, is equal to inverse of P slash minus M, right? Because you are bringing this on this side and this you are taking P slash minus M on the other side. And that's what is responsible for this. And this I epsilon is basically a reflection of the fact that instead of writing it as M square minus M square plus I epsilon, you could have also written it as minus M minus I epsilon whole square. Okay, it will put the I epsilon exactly in the same place. So that's why I have written this as 1 over P slash minus M plus I epsilon. Okay. So when you apply this, you will find that this becomes minus P square minus M minus I epsilon whole square. Okay. But that's equivalent to what we have here. Are there questions or comments? Okay, so let me proceed. So what you have written here is the same equation, except that we are thinking of now these things as matrices. Okay, so I have just dropped the alpha beta index. So you should really think of this as a matrix equation. Okay. So it's this equation, okay, or this equation, okay, with both sides alpha beta dropped from both sides. Okay, because I am not thinking of this. If I write SF without the index, that means you are thinking of this as a matrix. Okay, that's the convention. So this equation is the same as this, either this or this, where S tilde F is either this matrix or this matrix. So this is the analog of what we had defined for the Klein-Gordon theory as delta F tilde, or for the electromagnetism as D tilde. Okay, you remember we had defined D tilde mu nu or delta F tilde. So this SF tilde is the analog of that. And SF is the analog of delta F, okay, or D mu nu. So given this, now we can convert the, see how to draw Feynman diagrams. So as in the case of Klein-Gordon theory, the propagator will be denoted by a line. So SF alpha beta, okay, diagrammatically will represent by a line. But now there is a difference from the earlier case, because in the earlier case, okay, we are trying to calculate the time, the vacuum expression for the time ordered product of phi of x1, phi of x2. So both were phi, right? So there is really no distinction between the two ends, right? You don't have to say which end is phi, which end is phi, because both ends are phi. Okay. Here, however, when you are talking about SF, okay, if you have drawn a line, okay, then you have to say which end is psi, which end is psi bar, right? Because what we have here, the definition of SF is time ordered product of psi alpha of x1, psi bar beta of x2, right? It makes a difference whether you have psi or psi bar. Okay? This is not the same as psi bar alpha of x1 or psi bar alpha of x1, psi beta of x2. Okay? So you have to have some way of labeling which end refers to psi, which end refers to psi bar. Okay? And we'll do this with the help of an arrow. Okay? This problem is not specific to fermions, right? This problem will appear whenever you have a two-point function where the two fields are different. Okay? For example, for the charge scalar, if you have phi and phi star, okay, the same problem will appear. You have to say which end is phi, which end is phi star. So in any case, here our convention will be that we draw the arrow from the psi bar end to the psi end. Okay? And if you want to remember how, what is the insight behind this, you should just keep in mind that psi contains a annihilation operator for the electron, right? So it's as if the psi is absorbing an electron, okay, because it annihilates an electron. So this arrow you can think of as the direction in which the electron propagates. On the other hand, psi also creates a positron, so you can think of the arrow as opposite to the direction in which the positron propagates. So the fact that you have drawn the arrow along the electron propagation is just a convention. But once you have introduced this convention, we will stick to it. So whenever you see a fermion propagator with an arrow, we'll know that the psi index is to the left side of to the side towards which the arrow is going, and the psi bar index is the side from which the arrow is coming. Is this convention clear? Okay. So we can also define now the momentum space propagator. Okay, this will be the analog of what we had called delta F tilde P1 P2.
Sir?
Yes, go ahead, please.
Sir, this diagram of SF alpha beta,
Yes.
it's symmetric under x1 x2 exchange, right?
No, it's not symmetric under x1 x2 exchange, because yeah, it's not, because you just look at the definition, right? To change x1 and make this x2 and this as x1, right? It's not symmetric.
Okay.
Okay, so in general, yeah, it doesn't have any symmetry. For scalars, it was of course symmetric under x1 x2 exchange, because both ends were phi, right? And there's no other index.
It still has the symmetry that Under x1, x2 exchange and transpose it's antisymmetric.
Under x1, x2 exchange and transpose it's antisymmetric.
Yeah, SF transpose x2, x1 is minus SF x1, x2, right? No? I mean, that's how we defined it, right? In the first line of SF alpha beta.
Well, I mean, I don't know whether we'll call it SF transpose. Or maybe it. You're right. It's so what you have is psi bar beta psi alpha. Okay. If you exchange psi bar beta, if you make psi bar beta first and psi alpha on this side, right? Then that is minus of psi alpha psi bar beta. Okay, that there's a confusion. But SF transpose will mean what? That you are changing beta and alpha, right? That makes it psi beta of x2, psi bar alpha of x1, right? That's still different. So imagine that you are exchanging alpha beta and x1, x2, right?
Oh, yeah.
It will become psi beta of x2, psi bar alpha of x1, right? That's not the same.
Yeah.
Yeah, so SF doesn't have that symmetry. Okay, so SF you really should think of as having distinct properties in the alpha and beta index. Are there other questions? Okay, so SF tilde, okay, P1, P2, okay, as I was saying, is the double Fourier transform of SF x1, x2. So to the minus I P1 dot x1 minus I P2 dot x2. Okay. And now if you substitute this over here, okay, you will find that it's SF tilde P1 times 2 pi to the 4 delta 4 P1 plus P2. Okay. So in the momentum space, okay, we'll represent the propagator in this way, right? When you try to calculate the momentum space Green's function. Okay. So this convention that the P1 and P2 flows outwards, right? This is the same as the scalars. Okay, for the scalar propagator, if you remember, right, when we had represented the scalar propagator in the momentum space, okay, we had said that we will choose the convention that the momentum that this propagator carries, the two-point function carries, P1, P2, they will be drawn as outwards, okay, towards the external points. So that's still true here. Okay, so the momentum will be drawn outwards. We will not want to make a difference between scalars and fermions here. Okay, but this label will still be there. Okay, the two sides will be labeled by alpha and beta, and there will be an arrow, okay, which tells us which side is psi, which side is psi bar. So this propagator, so in the momentum space, we will represent the propagator this way, right? X1, X2 you have replaced by P1, P2, and this, the corresponding expression will be given by this, right? Because that's a Fourier transform. Yeah. Okay. So this is again an important point to remember, okay, that unlike scalar and vector propagator, the direction of momentum is important here, okay, because SF tilde of P is not the same as SF tilde of minus P, okay, because there is a P slash minus M sitting here, right? This is not invariant under P goes to minus P, okay, or this is not invariant under P goes to minus P. Okay. So again, let me state the rule. Okay, if the arrow points from beta to alpha, okay, let's imagine that you have a line like this, arrow points from beta to alpha. Then we look at the momentum along the arrow. That in this case is P1, right? Or minus P2. Okay. But P2 is opposite the arrow, P1 is along the arrow, right? So the momentum along the arrow is P1. Okay. This is the momentum that enters the argument of SF tilde. Okay. So here, for example, okay, it will be P1 slash plus M. Okay, so if somebody gives you a propagator like this, right, you have to know whether it's P1 slash plus M in the numerator or P2 slash plus M, right? And the rule that you are finding here is that it's P1 slash plus M. That means it's the momentum along the arrow. So this you should keep in mind. Okay, that's the way we have to evaluate the Feynman propagators. Okay, for when evaluating the Feynman diagrams for the momentum space propagators, this is the rule that you have to follow. Is this clear? Are there questions, comments? Okay, so I'll also leave it to you to check that these are identically 0. Okay, it's in fact reasonably simple. So let me just point out what happens. If you take psi, for example, you see psi has a B and a D dagger, right? So if you take two psis, right, then you either get two Bs, of course, that's 0. You get two D daggers, right? That's also 0. Okay. But you may get B and D dagger, okay, but that's also 0, right? Because B you can pass through D by picking a minus sign, and then the B annihilates the vacuum. Okay. So it's only psi bar that gives a non-zero two-point function. Psi two-point function is 0, and so is psi bar. And this you can also understand by charge conservation, because we have seen that psi picks up the phase e to the I theta, right? So this one will pick up a phase of e to the 2 I theta under that symmetry, right? The charge rotation symmetry, and that makes this 0, right? Because unless this is invariant, okay, we know that its vacuum expression value cannot be 0. That was the general result we had proven earlier. Similarly, this picks up a phase of e to the minus 2 I theta, okay, under charge rotation, and that makes this 0. So you can see it explicitly that these are 0, but you can also understand why these are 0 by using symmetries. Is this clear? Are there questions? Okay. So now let me tell you how to calculate a general Green's function. So once we have the propagator, okay, then we can calculate general Green's function. Okay, so the general Green's function that you want to calculate is of this kind. Okay. So here we have a set of psis and a set of psi bars. Okay. Again, it's easy to see that unless the number of psis and number of psi bars are the same, the result will be 0. Okay. So I have taken n psis and n psi bars. Okay, but the arguments are of course arbitrary, x1 to xn, y1 to yn. The indices are alpha 1 to alpha n and beta 1 to beta n. And so the general Green's function will have this structure. And by the same procedure that we did for the Klein-Gordon field, right, we can show that this Green's function can be evaluated, okay, by using Feynman rules, okay, which basically means that you join these vortices by propagators, okay, in all possible ways, okay, and you take the product of the propagators and sum up all the diagrams. So this is what I have said here, right? We can express this as a sum of Feynman diagrams. Okay. The proof I leave to you as an exercise, okay, is the same proof that worked for the Klein-Gordon. Okay. Basically, you write each psi in terms of B and D dagger, each psi bar in terms of B dagger and D, okay, and then you have to take all the B's to the right, okay, one by one, okay, and basically what you find is that you'll pick up the contribution from each pair at a time. Okay, and that's why it's given by sum of Feynman diagrams, okay, product of propagators. So the only difference is that the psis and psi bars have to be treated differently. Okay. So how will they be different? So psi will represent an external vortex with the property that a propagator connected to the vortex must have its arrow towards the external vortex. Okay. And that basically follows from this, right? That the end towards which the arrow is directed, that's the psi end. Okay. The end from which the arrow comes out, that's the psi bar end. Okay. So that's the rule you have to follow. Okay. That psi is an external vortex with the property that the propagator connected to the vortex has its arrow towards the external vortex, and psi bar is the external vortex with the property that a propagator connected to the vortex must have its arrow away from the external vortex. So a propagator basically connects a psi bar to a psi, but never a psi to a psi or psi bar to psi bar. Okay. So basically what you have is that you have n y's, okay, and n x's, okay, and you have to find all possible ways of connecting the y's to x's. Okay. So we take a yj beta j and we connect it to some xi y alpha I, okay, and you have to join all of these, okay, all the n, make sure that there are no free vortices left over. So that gives you one Feynman diagram. And then you have to sum over all possible Feynman diagrams, which basically means that you have to sum over all possible ways of making this connection. So in a generic term, what will happen is that yj beta j will be connected to some x, what I have called is x of pj, alpha of pj. So the notation here is the following. So p is some permutation of 1 to n, and pj denotes the jth element of the permuted numbers. So you take a particular permutation of 1 to n, and then you connect the y1 to x of p1, y2 to x p2, okay, y3 to x p3, and so on. And then of course the alphas and betas follow up appropriately. So this is then the formal expression for the Green's function. You sum over all permutations, and then so this is the sum over Feynman diagrams. And then for each Feynman diagram, we'll have n propagators, because you have n y's connected to n x's, right? N propagators. Each of these will have the form SF alpha pj beta j, because these two are connected. And then the arguments are x pj yj. And then there's an important sign factor that I'm going to discuss in the next slide. But is this structure clear? Is there any question about this? Maybe I can try to draw some, and then I can. So this, okay. So basically what happens is we have a set of points here, and a set of points here. See, these are the size. The left ones are the size, and the red ones are the psi bars. Okay. And then you have to join them, right? So I'll just give you one possible ways of joining them. Okay. So here, for this Feynman diagram, there will be 4 propagators. Okay. And then you have to take the product of those 4 propagators. Then there are other ways of joining it. For example, you can drop this, so these two, and join it across. Okay. So join. Okay, so this is another Feynman diagram. Okay. And you have to write the propagator for this Feynman diagram, propagators, the 4 propagators, and take the products and so on. Okay, but as I said, the more important an important point is that there is a sign factor that accompanies each of these. Okay. And these sign factors basically come because the time ordering has this extra minus sign in between, right? And that has to be taken into account. So I'll now discuss how exactly the sign factor is determined, and then I'll stop for today. So here is the general rule that we can follow, and you can prove this rule by simply starting from the definition. Okay. But I'll leave the proof to you, and I'll give the general rule. Okay. So let's suppose that you have to calculate this. Okay, a product of psi alphas and psi bar betas. Okay. So in a given term, one of the alphas will be paired with one of the beta j's. Right. So if alpha is paired with beta j, we connect them by some line on the top. Okay, let's imagine that suppose alpha 1 is paired with beta 1. Okay, then we'll take this and then connect it by a line like this. Similarly, suppose alpha n is connected to beta n, you will take alpha n and connect it by a line to beta n. Okay. And you have to do this for every pair that is connected by a propagator. Okay, so this is for a given Feynman diagram that we're calculating the psi. Okay. So for a given Feynman diagram, we have these alphas and the betas, we connect them in all possible ways. Okay, we'll connect them in the way it's given in that Feynman diagram. Then we count the total number of times the lines intersect. Okay, all these lines that you have drawn, you count the total number of times the lines intersect. And if this number is n, then the corresponding sign is -1 to the n. So this is a rule. Okay, as I said, this rule you can understand by going through the derivation carefully. But what I'll do is to illustrate this rule with some example. Okay, is this clear? Are there questions on these rules? Okay, so here is an example. Okay. Say a 4-point function, 2 psis and 2 psi bars. So this has two terms, right? SFR. So you could have connected alpha 1 to beta 1, okay, and alpha 2 to beta 2. That's one possibility. That's this one. Or you can connect alpha 1 to beta 2 and alpha 2 to beta 1. Okay, that's another term. Okay, that's second term. So now let's calculate the sign of this term. The first, here you are connecting alpha 1 to beta 1, right? So alpha 1 goes to beta 1. Okay, you can imagine this line. Okay, alpha 1 to beta 1. Okay. And also alpha 2 to beta 2. So alpha 2 goes to beta 2. Okay. So you can probably visualize that these two lines intersect once, right? Because this line goes like this and the other line goes like this. Okay, so that's one intersection. So -1 to the 1, that's the minus sign. This term has alpha 1 and beta 2 connected. So alpha 1 gets connected all the way to beta 2. Okay, so that's one line. And then alpha 2 gets connected to beta 1. So that's this. So here you see that the two lines don't intersect. And that gives you -1 to the 0, that's plus. Now it may happen that there are different ways of drawing this, right? For example, I could have drawn alpha 1 to beta 2 like this, and alpha 2 to beta 1, right? That goes up and then comes down, right? So in that case, it will intersect twice. But the result is still 1 because -1 square is still 1. So you can prove in general that while the number of intersections can depend on how you draw the lines, whether it's even or odd doesn't depend on how you draw the lines. Okay, so this is unchanged. This doesn't depend on how you draw the lines. So this is the general rule. Okay, so in general, of course, the expression that you have, the time order product that you have to calculate may not have all the size to the left of all the psi bars. Okay. So the first task in fixing the sign is to bring all the size to the left of all the psi bars. Once you have done that, brought all the size to the left of all the psi bars, then you can apply this rule. But during the process of bringing the psi bars size to the left of psi bars, you may pick up additional signs, right? Because every time psi crosses the psi bar or a psi itself, you pick a minus sign. That's because inside the time ordering, any exchange costs a sign if you are exchanging fermionic operators. Okay, so that's what I have said here. Okay. That exchange of any pair of fermionic operators produces a minus sign inside a time ordering. Okay, that just follows from the definition of time ordering. Okay. So we first bring all the size to the left of all the psi bars. Okay. But during this process, we may pick up some additional signs that you have to take into account. Is this clear? Are there questions?
Sir?
Yes, go ahead, please.
Sir, can you just draw this for 4-point function?
Okay, yeah, I'll draw this for 4-point function. Let me. Yeah, so one way to draw this. So 4-point function will be. Let me draw it this way. Okay, so there are two diagrams. Okay. One is this. Okay. and the other one will be okay. So these are the level of Feynman diagrams. Okay. Now let's look at this other pairing. So let's call this alpha 1, alpha 2, beta 1, beta 2, alpha 1, alpha 2, beta 1, beta 2. Okay. So now suppose we are trying to calculate psi alpha 1, psi alpha 2, psi bar beta 1, psi bar beta 2. Okay. So when you join alpha 1, beta 1 and alpha 2, beta 2, I am drawing alpha 1, beta 1 and alpha 2, beta 2. Okay. So this, you see there is one crossing, right, between the two lines. So this gives you -1. On the other hand, if we take psi alpha 1, psi alpha 2, psi bar beta 1, psi bar beta 2, then if we join alpha 1, beta 2 and alpha 2, beta 1, okay, let's say suppose you join like this. Okay. So number of crossings here is 2, right? It is 2. You could have also made it 0 if you had gone if the height was less. Okay. But this sign is +1. Okay. So in terms of Feynman diagrams, right? Let's see. So this is alpha 1, beta 2, alpha. Sorry, this is alpha 1, beta 1, alpha 2, beta 2. So that this one, right? So this one has the first diagram has a sign -1. Okay. The second diagram has sign +1. Is this clear?
Yes, sir. I was actually confused that whether I have to pick the sign of diagram or this field. Okay, fine.
Yeah. So for the diagram, so you draw the diagram that gives the expression, and to get the sign, you write the size in this order, and then join them by lines.
Okay, thank you, sir.
Okay. Any other question? So I'll advise you that you should practice it. Okay. Say for example, 3 psis and 3 psi bars, right? There'll be now 6 Feynman diagrams, right? That's a 3 factorial, because basically you can permute the 3 among each other. So you'll get 6 diagrams, and you should be able to write down the corresponding expressions and the signs explicitly. Okay, so this I'll advise you to check explicitly. Okay, how it works. Are there other questions? So basically, this will be the end of what I'll discuss about free Dirac theory. Okay. And next time, what we're going to do is to put together electromagnetism and the Dirac theory. Okay. It will be the sum of the Lagrangian of electromagnetism and the Dirac action, okay, and one extra term, okay, and that will be the coupling of mu to jmu, right? Because we had seen that when you try to reproduce the source term on the right hand side of the electromagnetic field equation, you have to add to the action a term proportional to integral mu jmu. Right? We know what jmu is, right? We derived it today. Okay? The expression for jmu. Let's see where we had. Yeah. Okay. So this was the expression for jmu. So we'll have the sum of the free Maxwell's action, free Dirac action, and then an integral of mu jmu. And then that is a theory that describes the interacting theory of electrons and photons. Okay, so that's the theory we're going to start studying next time. Are there questions?
sir.
Yes.
Let's say, let's consider this Maxwell's Lagrangian. That
Okay.
is gauge invariant. But
Yes.
let's say we are doing perturbation theory, and later we added some term that is not gauge invariant. So can we still do perturbation theory to find the answers, like to like, let's say, scattering matrix or anything?
Not really. See, if you in a gauge theory, right? If you break gauge invariance explicitly, typically the theory becomes inconsistent because the whole structure breaks down, right? You had argued that certain things decouple.
Yeah.
That the physical degrees of freedom, for example, is less than what you had to begin with, right? Because you can do this gauge fixing and so on. So even a small amount of breaking of gauge invariance will make the whole structure collapse.
Okay.
So it's important that in a gauge theory you never break gauge invariance. It may be spontaneously broken, right? That's possible, but there cannot be explicit breaking of gauge symmetry in a theory which has gauge symmetry.
Okay.
So that's a principle you have to keep following, right? You cannot even introduce even a small amount of gauge symmetry breaking.
Okay. So this problem is not there in when we couple this to Dirac field.
No, we'll see that
field to...
gauge invariance will be maintained exactly.
Yeah. Okay.
Okay. So basically, what will happen is that this symmetry that you see here, right? There you had an mu going to mu plus del mu lambda, right?
Yeah.
When you replace theta by lambda of x, okay, that will be the exact symmetry of the combined theory.
So there, the conservation of current, does that maintain this gauge invariance?
Yeah, in a sense that, I mean, okay, electromagnetism is somewhat simple, okay, that it works in a simpler way. Okay? So basically the point is we have this del mu j mu equal to 0, right? It's a conserved current that to which mu couples, right? That's going to be important. Okay. Now, typically you would expect that if you have del mu j mu equal to 0, that was a consequence of the free Dirac equation, right?
Yeah.
Now, once you couple it to mu j mu, then not only electromagnetic field equation changes, but the Dirac field equation also changes, because j mu depends on psi, and that changes the psi equation of motion. But what happens here is that the j mu still remains constant, even though the psi equation of motion has changed. So that's why you don't have to do any make additional effort to make this gauge invariant. It will automatically remain gauge invariant. But if you had done a similar thing, for example, for a charged scalar field, for a charged scalar field also you can construct j mu, right? Because if you have a phi and phi star, then there is similar phase symmetry there. Yeah. But there, if you just couple mu j mu, right, you will find that the phi equation of motion gets changed in such a way that it's no longer gauge invariant. It's no longer conserved, the j mu. And you have to add something extra to make it conserved. But for Dirac equation, it's simpler, right? We will see that that mu j mu term, right? Once you couple it, maintains the symmetry exactly.
Okay.
Sir, is this a comment on like adding a coupling in a way that this charge is still conserved?
Well, the general principle is that you have to add the coupling in a way so the gauge invariance is still maintained. And the conservation of the charge basically follows from gauge invariance.
Yeah. So in the scalar case, will the gauge invariance also not work just by adding the j?
No, it will not work just by adding mu j mu, right? You have to also add an additional term which involves two mu's and two scalar fields.
And that will take care of both at the same time, right?
Yeah,
Gauge
that will take care of
invariance
both
and this conservation of charge.
Exactly. That will take care of both at the same time.
Also, is this a generic feature of gauge theories that it's in the Lagrangian?
Sorry, Kaustuv, your voice is getting cut.
Yeah, sorry. Is this a general feature of gauge theories that in the Lagrangian, the theory is gauge, the manifestation of gauge invariance is present in the Lagrangian? Like, for instance, in A mu, we can straight away see in the equations of.
Yeah, you can see equation of motion. Okay, your voice again got cut, but let me try to answer anyway. Yeah, so basically, yeah, it's a generic feature that the action remains gauge invariant. What can happen is that there may be total derivatives, but it's a general feature that if the equations of motion are gauge invariant, then the way you will write the action is also gauge invariant.
Then could we have like let go of A mu altogether and write everything in terms of E field and B field, electric and magnetic fields, and quantize them?
Yeah, the point is it's hard to write a Lagrangian in terms of E and B unless you put some additional constant, because the divergence of B equal to 0
Yeah.
has to be then put in explicitly, right? I think I don't think there is any way to write a Lagrangian, okay, which is manifestly Lorentz covariant and which uses E and B as fundamental fields.
Okay.
Okay, so that's why one uses this A. Also, I mean, in a sense, A is needed to couple to charges, okay, because the coupling to the charge is A mu J mu.
Yeah.
And you can also see that, I mean, in a sense, there are observables which are not directly, which do not look, at least the local expression in terms of E and B, which are what are called Wilson lines. If you take integral of A dot dx
Yeah.
along a cycle, that's also an observable. And it's not always writable as in terms of E and B. Okay, particularly the manifold has holes, for example. Imagine that you have a two-dimensional plane with a hole.
Okay.
And you write integral A dot dl along the hole, around the hole, right? Then you cannot write it just as a magnetic flux on the two-dimensional surface, right? Unless you also specify what happens inside the hole.
But are you saying that this still is a well-defined quantity? The integral along the
Yeah, the
contour.
integral is still well-defined quantity because it will be gauge invariant.
Okay, but it's okay.
Okay, but it's not writable as surface integral of.
Observable.
Yeah, it's an observable.
Okay.
But locally, of course, yes, electric and magnetic fields constitute the full set of observables. Nevertheless, I think it's hard to write a Lagrangian or an action in terms of E and B. Unless you put additional constants.
Yeah. If we were to suppose do that, like take the divergence B equation separately, will Dirac's procedure give us these results? Like eventually we are writing the F mu nu F rho sigma time ordered product inside the vacuum in some D mu nu, which were further written in terms of A mu and A nu.
Yes.
So and F mu nu and F rho sigma we can write in E and B form.
Yes.
So like we can eventually compare if we did indeed have a theory where we would start with E and B only.
Yeah, but the point is, if it's just integral E square minus B square, right?
Yeah.
You can see that doesn't give the Maxwell's equation. Right? If you vary with respect to E and B.
Okay.
Right? You're not going to get Maxwell's equation. Right? You will get E equal to 0 and B equal to 0.
Yeah, that won't work.
Yeah. So
okay. I mean, okay.
yeah, so you can probably do something very complicated, introduce auxiliary fields, etc. Right? But this certainly is the simplest way to formulate electromagnetism. Right? Just introduces a gauge field, which is independent degree of freedom. It has, I mean, the only thing is that it has some redundancy, right? Because A mu and A mu plus L mu lambda gives the same set of fields. But nevertheless, this is, I think, the most economic way to formulate electromagnetism. electrodynamics.
Yeah. Also, can there be some hypothetical consideration of fields, or in that way the particle which does not really behave by a single Lorentz transform, like in the sense that under certain conditions it may act as some scalar, and under certain other conditions it may act as a
Well, the point is, the particle spectrum is controlled by group theory, right? I mean, since the Lorentz transformation form a group,
yeah.
I mean, whatever you observe must be a representation of the group, right? And that you cannot alter, right? So everything has to be classified by the representation of the Lorentz group. So it cannot be that something behaves as scalar in some cases and vector in some other cases, right?
I mean, it would translate to saying that we are adding in Lagrangian for the same particle two terms, one of which looks like a scalar and the other of which looks like a spinor equation, which will give the spinor equation. But they are
But then
actually
the point is that,
corresponding.
yeah, but then the Lagrangian will not have any symmetry at all, right? Lorentz invariance will be broken. Because to get a Lorentz invariant Lagrangian, you have to assign a particular symmetry transformation. And you are saying that one set of terms is invariant under that symmetry transformation, the other one is not. But that means that the full Lagrangian doesn't have the symmetry at all.
Yeah. I mean, okay, so, consider this like we have a phi square theory, like a scalar theory, plus this free electron theory.
Yes.
Which we are representing by psi.
Yes.
Eventually, I'm saying all the observables correspond to some single particle. I mean, this is not a very good statement.
Meaning your case matrix involves in states and out states, which are formulated in terms of single particle states. Yes.
Yeah, and I'm not distinguishing between those particles also.
But you can, right? You can measure the spins of those particles. So I mean, you may not choose to measure it, but you can measure it, right?
Yeah, in this case, this is directly in front of us, but it might not be a priori known what observable to measure.
Well, see, I mean, we certainly know that, I mean, you can classify particles on a Lorentz group. As long as the Lorentz symmetry is the symmetry of the theory, right? And that, I mean, there is no reason so far to believe that it's not. Then you can classify the particles by how they transform on a Lorentz group, right? And that information is part of the information about the particle, right? Whether or not you choose to look at it.
Yeah.
Yeah, so I don't think there is any way that you can think of the particles as both scalars and vectors. Right? There will be distinct particles.
I think, I mean, what he was trying to ask is, let's say we have two terms in the Lagrangian, and like one is the Dirac Lagrangian term, and other is like, let's say, a scalar term, scalar field term, and still when we compute the propagator, we have only one pole in the Green's function. So that,
that can happen.
Correspond to,
that will not happen in perturbation theory, right? But in QCD, for example, that's what happens. That you have a lot of Dirac fields, but you don't see those Dirac fields poles in those Dirac fields. Right? So certainly that can happen. I mean, it's not necessary that the fields that you introduce in the Lagrangian are the ones that you see as poles in the Green's function.
Yeah, so I'm saying that there won't be a way. I mean, a priori, we don't know a way of distinguishing such particles from other particles.
Meaning bound states from elementary particles. Is that what you are saying?
I mean, either that way, or let's say what Harshit is saying, we have two fields, one psi, this Dirac field, and one scalar field, but at the same. So there will only be one, and they are both free theories. They aren't coupled to each other either. So we'll only see one pole, right?
No, you'll see two poles.
but they are at the same point.
Well, but upon in one case, you will see the pole as in the scalar propagator, in the other case in the fermion propagator, right? You're saying they have the same mass. So let's admit that they have the same mass. Right?
I mean, both of these correspond to the same observable.
No, they are different two-point functions, right? One is a scalar two-point function, one is a fermion two-point function.
Yeah, I mean, theoretically, I'll write them on paper, but when experimenting with some scattering amplitude or however you measure mass, I don't know in experiment, but
Yeah.
I'll just get one number out of it.
Oh, yeah, but you'll get one number, but in different experiments, right? And you will know that they are referring to different particles from various experimental signature, right? I mean, there can be degenerate particles of the same mass, but there is a way to distinguish between what are the particles, because see, it's not that all the properties are the same, right?
Yeah, not all of them would be same if they are actually two different particles.
Yeah, exactly. Right. So if you find that the other properties are different and the masses are the same, then they are certainly different particles. Right? Even if the other properties are the same, suppose you have a Dirac fermion, right? I mean, there is a rotational symmetry that turns an up electron into a down electron.
Yeah.
But you can still distinguish them, because when you take the two particle state, for example, right? Then you know the two particle states, there can be two electrons, two up electrons, two down electrons, or one up electron, one down electron, right? So you'll be able to distinguish between two up electrons from one up, one down electron. Okay. I mean, one can go into a singlet state, other one can go into a triplet state. And this will tell you, the fact that these two have different properties will tell you that you actually have two different kinds of particles, right? Not two electrons in the same state. They're not two identical electrons.
Yeah.
So whenever you have multiple, I mean, in the same pole, but with different particles, right? Then at the level of multi-particle state, you can certainly distinguish them. Right? Even if the at the level of the single particle, there is a symmetry that relates them.
Okay.
Yeah, so certainly different elementary particles can be distinguished. Okay? In principle, of course, I mean, in experimental, you have limitations, right? And it has happened in the past that people, I mean, two particles people who thought were different turned out to be the same.
Which were
But
those?
once you have enough data, right, then you can see whether the particles are the same or not.
Like, why would this happen? I mean, what happened in this case?
Well, what happened was that the people, I mean, people had seen decays, that same particle, the particle had the same mass, right, but it had different decay channels. And if both decay channels were to be attributed to the same particle, then you know that you would have to give up some symmetry, right, parity.
Okay.
And or in this case CP, for example, and the point is, people didn't want to give up any symmetry, right? So they thought they're actually different particles, because the same particle, if they have two different decay channels which have different symmetry properties, right? Then how can that be? Because I mean, the same particle cannot have both parity odd and parity even property, right? But if the symmetry is broken, then of course it can happen. Right? And finally, that's what happened.
Okay.
So due to experimental limitations, you may be able to let to think that two particles are the same or they are different. But once you have enough data, you can certainly distinguish between whether the two particles are the same or different. Okay, I guess the probably next class will start soon, so I should stop. So tomorrow there will be no class, and the next class will be next week. Okay, so I'm now logging out.